Hello everyone, this is Zhiqing Liu from National Taiwan University. I'm now introducing a work named Samples Rectification for Unsupervised Cross-domain Person Re-identification. This is a collaboration work with Manyu Li, Zaixian Chen, and Xiaoyu Jian in National Taiwan University. What is person re-ID? Given a query image, we want to match the images in the gallery set of same person captured under multiple cameras. The common way is to train a CNN with classification laws, where each ID is a class. However, the challenge for supervised learning method is that it is hard to annotate persons across cameras, and it is also unrealistic to deploy in a real-world scenario. Recently, many works focus on unsupervised cross-domain setting, where given a labeled source dataset, we want to learn re-ID on an unlabeled target domain. And recently, most works adopt the clustering-based method to solve the problem. They will first pre-train the CNN with labeled data. Then they can use the CNN to extract features of those unlabeled data and perform clustering. The clustering results are the pseudo labels. We can fine-tune the pre-trained CNN with the target data and its pseudo labels. However, there are some problems in clustering-based method. The first one is the same identity pairs captured under different cameras with intensive variation of the appearance could be possibly misclustered to different groups. We call the pair hard positive. The second one is different people with similar appearance are often clustered to the same group. We call them hard negative. Those pairs will decrease the quality of clustering results and furthermore degrade the discriminative ability of CNN model. Thus, our goal is to rectify those hard samples in the clustering results. We propose an inter-camera mining technique called ICN, which can rectify the positive samples, and the part-based homogeneity technique called PBH, which can rectify hard negative samples. Our two techniques are added on the clustering-based baseline framework, which is iterative learning of clustering and CNN training. At the beginning, the CNN will extract features and perform clustering, which are some algorithms that do not need the number of clusters first. Then the data in the same cluster are assigned the same pseudo label. The labels are used to train the classification laws to fine-tune the CNN extractor. We also adopt triple loss. Given an anchor image, we hope that the feature distance of the positive pairs is smaller than the negative pair. In our implementation, we adopt a variation called weighted triple loss. So let's first introduce the first technique, inter-camera mining. And just as mentioned before, the person under different cameras are usually clustered to different groups. Thus, the CNN training will always optimize on those similar positive pairs. Although we cannot know the true label of the image, we can additionally mine possible hard positive pairs, which are the same ID pairs with different cameras, to shorten their feature distance. So let's step by step to describe our ICM algorithm. For each unlabeled target image P, we will rank other images by feature distance. Then, because we define that the hard positive pairs are those captured under different cameras, we remove image under those cameras as image P. Then we hope that the chosen images are the real hard positive pairs. Thus, we select top K similar samples to form the rank P list. To increase the robustness, we propose and adopt the top K base body pairs technique. Only if image P is also in the rank list of images in rank P, the pairs can be regarded as the hard positive pairs. For example, image P is in the rank list of image number 3. Thus, image 3 and P are best buddy pairs. However, P is not in the rank list of image number 6. Thus, we will remove image number 6 in the rank list P. The mined hard positive pairs will be used to additionally optimize the ZN network with triplet loss, called ICM loss. Note that in ICM loss, the negative pairs are images not in rank P and with different pseudo labels to image P. Let's introduce the second technique called power-based homogeneity. The problem is that different people with only subtle difference are possibly grouped into same cluster. The goal is that we want to partition off the imperfect cluster that contains hard positive pairs. We first define the imperfect cluster. Because we didn't know the true labels of images, we can only use the Selway score to measure the quality of cluster. For image I, AI is average distance to I within the same cluster. BI is average distance to I within the closest cluster. So this is the equation of the Selway score. And for a cluster, we calculate the mean Selway score of each image J. So how to define the imperfect cluster? For cluster, if the mean Selway score is smaller than the threshold, we call that the cluster is imperfect. Then, given an imperfect cluster, we try to cluster the image inside. We split each image feature into upper and lower branch. And the upper feature and the lower feature can represent some fine-grained feature. And for the upper part, we use the K-means algorithm to cluster to 2 groups. For the lower part, we also use K-means algorithm to partition to 2 groups. Thus, there are 4 types of combinations, and we can at most split the imperfect cluster to 4 groups. So this is overall architecture. First, for each iteration, we first do cluster to create pseudo labels. Then our PBH will try to split the imperfect cluster, which contains hard negative pair. It will refine the original pseudo labels, and those pseudo labels will be used to optimize triplet loss and cross-entropy loss. At the same time, we also adopt our ICM. It will mine the hard positive pairs to pull close the feature. Okay, so this is our overall architecture. The experiments are conducted on 2 widely used datasets, the Market 1501 and Duke MTMC ReID. And the evaluation measure, we use the rank 1 accuracy and MAP, mean average precision. Okay, so we can see the experience results. We first introduce what is the meaning of the table. Duke to Market means that the label dataset is Duke. So we can pre-train the pre-trained model on Duke and then deploy on the unlabeled dataset Market. So the vice versa. So the first line, direct transfer, means that we only use the pre-trained network to directly test on the target unlabeled dataset. And the baseline is our iterative cluster and training pipeline without the ICM and PBH. Then we add the baseline model with PBH. And with our PBH, it can refine the pseudo labels and increase about 1 to 2% in terms of MAP. Then with ICM, it can increase about 60%. This line means that the baseline model with ICM loss, not with PBH loss, PBH technique. So with ICM, it can increase about 60%, and with the 2 methods, it can perform best. So let's compare to the state-of-the-art method. Those methods are all clustering-based methods, and we can see that our method outperforms them. So let's make some conclusion. We proposed an inter-camera mining technique to mine potentially hard positive samples. Then we proposed a part-based homogeneity technique to partition off the imperfect clusters to contain hard negative samples. So we conduct extensive experiments and achieve state-of-the-art on 2 benchmarks among existing unsupervised method. This QR code is our paper, and thanks for listening. Those are the reference. Thanks.